So this lesson, there's a lot in this lesson, and these are all SOLs that, you know, we're supposed to address, and they kind of come up right at this point now. We're going to start in 5.7. We're going to go back to 5.6 just a little bit, and then we'll jump back to 5.7 to finish it off. There's one or two slides that are fairly busy. I'm just going to say, please don't copy it all. If you want to copy it, go to the book. You know, it's just right out of the book. And if in a full day like this, if we sit around waiting for every little plus and minus to go in there, you know, we won't get done. In fact, there's very little opportunity to do the U-tries today. It's more just kind of an explain the process kind of day. But I mean, this one, you know, I always like the title of this lesson. It's in every Algebra 2 book and course. The fundamental theorem of algebra. Not a fundamental theorem, or not just a theorem, but this is the fundamental theorem of algebra. And actually, there is the fundamental theorem of arithmetic. And it may sound silly, but this is the fundamental theorem of arithmetic. Given two numbers, A and B, either A is greater than B, A is less than B, or A is equal to B. That's the fundamental theorem of arithmetic. The fundamental theorem of algebra is that if you have a polynomial of degree n, what does degree mean again? The degree of a polynomial is the highest power term, right, is the degree of the polynomial. If it has a degree of n, then it has n zeros. Exactly. Now, some of those zeros might be real numbers. Some of those zeros might be imaginary numbers. But if you add them up, the number of complex zeros is n. Exactly. Right? You don't want to overthink that one. You know, you're given a polynomial, you look for the highest power, that's how many solutions there are. Now that includes repeated zeros. You know, for example, if I had a, can't tell what's going on here, but let's say I had, you know, x squared minus 4x plus 4 equals 0. You know, that would tell us that we have two complex zeros. Well, that's a perfect square trinomial, so it's x minus 2 squared. You know, when we were doing that by calculating discriminants, we would have gotten 0 for the discriminant. We would have said one real zero, but we have to count it twice. So we would say this is x equals 2, and it's twice because it's coming from a factor, which is squared. Okay, so that's what they mean when they say including repeated zeros. So again, this is from the first example in 5.7. How many solutions, right? They use the word solutions because this is an equation. They might have also used the word roots, right? But how many solutions does this have? Given that the degree is 3, how many solutions? 3, right? Now they use the term zeros because this is a function, right? A function has a graph. So we're saying, well, that's actually not pertinent. But in a function, you're trying to find the values of x that will make f of x equal 0. How many do you expect? 4, right? It's that easy. So we'll do, this was the one you tried that I got in there. So the first one has how many solutions? The first one has 4 solutions, and the second one has how many zeros? 3. Okay. Really tricky stuff. Okay. Now, remember, complex zeros is the big set of, complex numbers are the big set of numbers. Real numbers are a subset of complex numbers. They are the particular case that when the a plus bi, which is a standard form for a complex number, the b equals 0. Right? That's just a particular case. If the b does not equal 0, you get imaginary numbers. Real zeros show up as x-intercepts on a graph. Right? Real zeros are x-intercepts. So real zeros are x-intercepts. So most of what we do in the lesson today is trying to learn something about the different kinds of zeros that we might get. Rational zeros, again, what's a rational number? Yeah, as a ratio or a fraction, right? So rational zeros, irrational zeros, usually unresolved square roots. Imaginary zeros means it's got an I in it. We have theorems for each one of them. That's what we're doing today. The only one you can do synthetic division with is this one right here. So really, our goal usually, we take a higher degree polynomial, we try to find a zero. Remember in the last lesson, we didn't know how to find that first zero. They gave it to us, and then we finished once we knew it. But here we're going to figure out how can we find what the first zero or first few zeros are so that we can reduce the polynomial, eventually get to a quadratic, and finish it with quadratic formula if necessary, right? So the only one we can do synthetic division with is this one right here. So that's the first focus of what we do. It is called the rational zero theorem. And this jumps back to 5.6, right? Now, I think usually kids your age, you just look at this like as a bunch of gobbledygook kind of stuff. In the end, it's not that complicated. What it's saying is, if there are rational zeros, they have to be of the form the factors of the constant divided by the factors of the leading coefficient. And every textbook always uses P for the constant and Q for the leading coefficient. P over Q. So you hear people talk about P over Q, P over Q. I don't, but it's like you can't avoid P over Q. And understand, because this has come up, I don't remember if it's this class or another class, that when you have a subscript like A1 or A0, that's just a constant. That's a way of designating a different constant. It's not mathematical. It's not like saying a superscript, which is an exponent. Now that's mathematical, right? But this is just a way to designate a different constant or a coefficient, right? That's a constant. These are all coefficients. So if we look at an example of this, you'll see exactly what we mean, right? If I want to find a list of possible rational zeros for this polynomial right here, then I'm going to take the factors of 12 and divide them by the factors of 1, right? So you have to think, okay, what are the factors of 12? And the factors of 12 are 1, 2, 3, 4, 6, and 12. Now, I can get 12 by multiplying 1 times 12, or by doing negative 1 times negative 12. So whenever you put a number in this list, it's going to be plus or minus. Right? You can always get there by doing positives or negatives. So that's why they have plus or minus in front of everyone. The factors of the leading coefficient, in this case it's 1, which means that really it's going to come down to just the factors of the constant, right? Because when I divide these numbers, anything divided by 1 is itself anyways. So this is going to be our list of possible rational zeros. Now, how many total complex zeros does this polynomial have? We just did it. How many complex zeros? It has 3. How many numbers are in this list? 12. If you include the plus or minus, there's 12. So clearly these are not all going to work. And it's possible that none of them work. Right? It is possible. But if we had to check, we would start doing synthetic division with those 12 numbers. And in my time, we would do synthetic division. Sometime, dozens of synthetic divisions to find the one that works. And we'd have pages and pages of this stuff. We're not going to do that. There's a little bit of it, in the lesson today and in the homework tonight, but not too much. So most of the questions that you might get with this will say, list the possible rational zeros. Finish. That's it. Can you make that list? Now this one's a little more complicated because the factors of 10, 1, 2, 5, and 10, have to be divided by the factors of 4, and now there's more than one, right? 1, 2, and 4. So to make our list, we have to divide 1 over 1, 2 over 1, 5 over 1, 10 over 1, 1 over 2, 2 over 2, 5 over 2, 10 over 2, right? You got to go through all the possible combinations of these numbers divided by these numbers. And that's what this list is right here. Okay. Now, the final list, they've thrown out repeats because 1 over 1 is the same thing as 2 over 2. You don't need to repeat it. 1/2 is the same thing as 2/4. 10 over 2 is the same thing as 5 over 1. So when they've thrown out all the repeats, this is the list. These are the possible rational zeros. And now we've got 8 numbers, and they're all plus or minus, so that's 16. 16 that you would have to check. And like I said, in my day when we didn't have a graphing calculator, then we would start running down the list. Now, we had a few theorems to help us with that, which 2 of them I see are not even in our book. One of them is, but I don't really use it much. Because usually what you do these days is once you've got this list, you look at a graph. You know, put it in your graphing calculator and see if you can find the x-intercepts that are close, and then do synthetic division, see if you get a remainder of 0. I mean, sometimes it looks like it's a rational number, and it's not. It's actually irrational. But you don't know that unless you do the synthetic division and test it out. You okay, Chloe? Okay. So try to find a list of possible rational zeros for the second one, right? Yeah. How about that? Anybody get anything more than that? Did anybody have 6 over 2? Or what was the other one? 2 over 2? Right, you would throw those out because you already have that, right? 6 over 2 is 3 and 2 over 2 is 1. So we should have had these numbers. In the book, they try to make a distinction between when you have a leading coefficient of 1 and when you don't. Obviously, it's easier if the leading coefficient is 1, but the main thing is rational zero test, do the factors of the constant divided by the factors of the leading coefficient. What if there is no constant term? What if the last term is a linear term? Then you'd need to divide out the x, and then you would have a constant in the parentheses. Okay, so that tells us the rational zero theorem. Now the next few slides are like one example in the book, and I'm kind of revealing it just a little bit at a time to kind of show the process that we go through. So it says, I think this is coming from 5, 6. Find all the real zeros, right? Well, how many complex zeros does this have? It has 4. That doesn't mean they're all real, but it has 4. So the starting point would be, okay, well, let's make our list of the possible rational zeros. And that'll be the factors of 12 divided by the factors of 10. And that'll be quite a list, right? Because there's a lot of factors of 12 and there's a medium number of factors of 10. So step 1, if you're making your list, that's the list. And again, if I count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 2, 32. There's 32 possible rational zeros. Right? In today's world, again, we don't just start doing synthetic division 32 times. We're going to look at a calculator and see whether we can see any x-intercepts that look like they're close to any of these numbers. And you can see that it looks like it's the graph has got 4 real zeros because it's crossing the x-axis 4 times. And some of these look like they might be close to some of these numbers. Like in between -1 and -2, that would be -3/2. So that might be one to check. In between 0 and -1, well, that could be -1/2. It might also be -3/5. Right? And then there looks like it could be a +1/2 or a +3/5. And this one, in between 2 and 3, how many of these numbers? 12 over 5 could be, right? And then there's some of these numbers that there's no reason to check at all. If you know that all 4 are in between -2 and +3, then you don't need to check this, not even this, right? There's a whole bunch you could just throw out because they're not going to be in the list. But generally, the process would be use the graph to help you get started. And I'll starting on the left. I'm going to try the -3/2, right? If I get a remainder of 0, then I'll know I found one of them. And sometimes you don't even have to get to the end of the synthetic division. You can see you're not going to get 0, and you just abandon it and go to the next one. But let's see. My coefficients are 10, -11, -42, 7, and 12. And I'm trying -3/2, so I put that in the bracket, and I bring down a 10. And now I do synthetic division. -3/2 times 10, right? 2 goes into 10 5 times, so that's -15. Do I have that right? -15. Add them up, -26. -3/2 times -26. 2 goes into 26 13 times 3 would be 39, and that would be a positive. -3. -3/2 times -3. -9/4. No, +9/4. 9/2, sorry. And I add them up, now I'm getting things like 16.5. And there's no way I'm going to multiply that and get a 0 here. So that's not working. Let's try the next. Let's try -1/2. -3/2 didn't work. Let's try -1/2. I think I've got it. Another blank slide here. Okay, I got a slide with more room. 10, -11, -42, 7, and 12. Right? Those are the coefficients of a 4th degree polynomial. I put -1/2 and -1/2 times 10. -5, -16. -1/2 times -16, 8, -34. -1/2 times -34, +17, 24. -1/2 times 24, -12, 0. So yeah, we found one. -1/2 is one of the zeros. Now, I not only found the 0, I just reduced the polynomial, right? It was a 4th degree. These are the coefficients of a 3rd degree, right? Now, our ultimate goal is, if we can get it to a quadratic, we can finish it. Quadratic formula always works. So I'm not going to drag it out. If we check the next one, we don't need to find try that one, because we found the one in between 0 and -1. It was -1/2. And I believe 1/2 doesn't work. 3/5 does. So let me do that. And now, here's the thing. When you divide out, I don't need to go back up to the coefficients of the 4th degree polynomial, right? I can use that row of numbers that I just made. If 3/5 was a 0 of the first polynomial, we didn't divide it out yet. It's still a 0. So I'm going to go like this, 3/5. 3/5 times 10 should be 6. Add them up. 3/5 times -10, -6. Add them up. 3/5 times -40, -24, 0. So 3/5 was another 0. And now these are the coefficients of a quadratic. 10x squared minus 10x minus 40. And if I want to find the solutions that come from that, that means that I'm trying to find the zeros, which means I can divide out the 10, right? Just divide it out. You don't need it. X squared minus x minus 4 equals 0. So then you look at that, if those other zeros are rational zeros, then this is factorable and you'll find it that way. Is it factorable? Are there factors of -4 that add up to -1? No. So it's not factorable, so how are you going to have to solve that? Quadratic formula, right? So that's always the end. Let me see. I think the next slide is probably x squared minus x minus 4. X squared minus x minus 4. So this will be x equals 1 plus or minus the square root of 1 squared minus 4 times 1 times 4, which is plus 16, divided by 2 times 1, which is 2. So x equals 1 plus or minus the square root of 17, divided by 2. So the last two are irrational, but they're real. So that is the process of, how you do, how you generate a list of possible rational zeros, use synthetic division to reduce it, and then finish it off. Now, in the homework, there's a few problems that are list the possible rational zeros. There's a few that say find the real zeros, but there's not that many in your list of possible rational zeros, so definitely use synthetic division, see if you can figure out which ones they are. You won't have the benefit of a graph unless you have a graphing calculator, but there's not that many to check. This now jumps to the last section, 5.7. And this is a 5th degree polynomial, so how many complex zeros do you expect? 5, right? And this is a graph, and how many real zeros do you see? You see two numbers here, right? 2 and -1. But remember, just like when we had a perfect square trinomial, on the graph, that was a parabola that just touched the x-axis and it went back in the same direction. Why? Because the factor was squared, it didn't change sign when it got to the other side of the 0. So when you see that kind of signature on the graph, what it means is the 0, -1 must be coming from a factor that is at least squared. That's why it's not changing sign after it hits the 0. So this one is probably coming from x plus 1, because that would be the linear factor, squared, but it's got a negative in front. That's why it's actually opening down. Right. So that's what it looks like when your factor is raised to an even power. That's what it looks like when your factor is raised to an odd power. So we could tell pretty well that this is probably, I can do synthetic division with using 2 once, and I can do it using -1 twice. That should work for sure based on this graph. And starting with a 5th degree polynomial, what will I have after I've divided out those 3 zeros? A quadratic, and I'll be able to finish it that way. No matter what it is, I'll be able to finish it. So we do synthetic division 3 times. All right, so here's my coefficients. 1, this is a big one. 1, -4, 4, 10, -13, -14, and erase. And in the bracket, I'm going to use 2 as the first one to start. 2 times 1. 2 times negative 2. 2 times 0. 2 times 10. 2 times 7. So sure enough, 2 is a 0. We knew it, but we got the zeroed remainder that we were looking for. Now on that set of numbers, I'm going to use negative 1. Right? Bring down a 1. Negative 1 times 1. Negative 1 times negative 3. Negative 1 times 3. Negative 1 times 7. And 0. Good to go. Right? Okay, now because of the graph, because I can see that it actually is touching that 0 and going back, I'm going to do negative 1 again. Right? And that'll look like this. Negative 1 times 1. Negative 1 times negative 4. Negative 1 times 7. 0. And there we go. That divided out also. So I started with a 5th degree polynomial. Dividing out 2 gave me a quartic. Dividing out negative 1 gave me a cubic. Dividing out negative 1 again gave me quadratic. So the quadratic is x squared minus 4x plus 7. And if I'm going to solve that, again, first question is it factorable? Are there factors of 7 that add up to negative 4? No. So what are you going to do? Quadratic formula, right? Your best friend, quadratic formula. I don't think I have this on the next slide, do I? No. So I'm going to run through it just because it shows something anyways. X equals 4 plus or minus the square root of 16 minus 28 divided by 2. X equals 4 plus or minus the square root of negative 12 divided by 2. So what kind of solutions are we going to get? They're imaginary, actually, right? So we see these 3, and we might think, well, there could be 5. Maybe like not in the view of this graph. Maybe over here it comes back around, or over here it comes back up. But no, it doesn't, right? Because the last 2 are imaginary. They're not x-intercepts. And this can be simplified, right? 12 is 4 times 3. So completely simplified. It's going to look like this. First step will be 4 plus or minus 2i times the square root of 3 over 2, which is 2 plus or minus I root 3. So there's our 5 zeros. 1, 2, 3, 4, 5. And that's what we expect, 5 complex zeros. Next. So that was, everything was about rational zeros, really. Now we get our 2 theorems that relate to, they say complex, but let's just say imaginary, and irrational zeros. And they both of these kind of say the same thing, which is you're never going to have just one imaginary zero. They're going to come in pairs, right? If you get a plus bi is a 0, then you've got to have a minus bi. And as far as irrationals go, if you have a plus the square root of b, then you're going to have a minus the square root of b. And I put this here, right, the quadratic formula on there, because again, where do either imaginary or irrational zeros come from? They come from right there, right? They come from taking the square root in the quadratic formula. And what's in front of the square root? The plus and minus, right? So that's why you're always going to get 2 of these. You're always going to get 2 of these, provided, and they say this in the irrational conjugate, provided that the coefficients of the polynomial are rational, right? I mean, if you had a square root in as a coefficient, well, then you could have 1, but we usually don't. We usually have polynomials that have rational coefficients. But that's why. So that gives us something that helps us to understand how many zeros we're looking for. I mean, even take on the last problem, right? We knew that it had 5 zeros. We could see 2 that were real numbers. But if 2 were real, or if only 2 were real, then how many would be imaginary? 3. But you can't have 3. You can only have an even number. So that was never going to be the case. It had to be that one of those zeros was repeated, so that they add up to 5 and you have an even number of imaginary. Okay. So the first problem, we're going to go through probably 3 of these anyways. And this is a very typical question that you can get on SOLs, definitely in just your regular old homework, which is, here's some zeros, make the polynomial that came from them. And the strategy is, first you take the zeros and you turn them into linear factors. Right? We've been doing this for a couple days now, right? What's the linear factor associated with the 0 of 4? X minus 4, not negative 4, right? What's the linear factor that is associated with 0 of 2? And what about negative 1? X plus 1, right? So you do that, right? You go X plus 1, X minus 2, X minus 4. But then you got to multiply them, which is, by the way, part of our quiz today. How do you multiply 3 factors? You start with 2, right? Start with any 2 you want, and multiply them together. And let's say if I do the last 2, x squared minus 6x plus 8, I still have to multiply times x plus 1. How do I do that? How do I multiply a binomial times a trinomial? Say again? I mean, that we saw the book gave us 2 methods, vertical and horizontal, and then I gave you that grid or lattice. I think somebody called it a lattice. Whatever way you can, you just got to make sure you've multiplied every term in this set of parentheses times every term in that set of parentheses. So the grid works. X plus 1, x squared minus 6x plus 8. Fill in the grid. X to the third minus 6x squared plus 8x. X squared minus 6x plus 8. And then combine like terms. Right? X to the third minus 5x squared plus 2x plus 8. So in a way, the guts of what you have to do here, we learned that when we did the multiplying. All we're learning really now is how do you go from the zeros to the polynomial, and you just turn those into factors, multiply. Okay, but the point of presenting these right after we just presented those theorems is that usually the way you'll get this is you'll be given a list like this. It's got one real number and it has one irrational number, it has one rational number and one irrational root. But based on the theorem, we know there's another irrational root. What is it? 1 minus the square root of 5. So you have to add to the list. One of the released SOL tests that we've used in the past couple of years, I mean, the question that had to do with that is they said, here's 1 plus the square root of 5 is a solution to a polynomial equation. What's another? And then it just had a list of 4, and the other one was 1 minus the square root of 5. You just had to pick it out of the list. You actually didn't have to do any of the math. You just had to recognize, right? So I would go like this. 4, there's 1. There's the second one, And now we've got a third, 1 minus the square root of 5. Okay, now we need to turn those into linear factors, right? Okay, the 4 is easy, x minus 4. Okay, again, how do you make a linear factor out of a 0? You do x minus the 0, right? That'll look like this, x minus 1 plus the square root of 5. X minus 1 minus the square root of 5. Okay, now we're at the point where we were when we had our 3 factors here, and we said pick any 2 of them and multiply them. Here you don't pick any 2 of them. You definitely want to pick these 2 to be first, because when you multiply them, because they're conjugates, all the irrational numbers will cancel each other out. Right? And you want that to happen. You want that to go away. Now I'm going to show you 2 ways to do it. And I'm sure after I show you the second way, you'll say, well, I'm going to do that. I'm not going to do this. But I would do this with a grid. You know, with the same grid. I mean, I'll take a step and I'll distribute the minus. X minus 1 minus the square root of 5. X minus 1 plus the square root of 5. Right? So that's going to be, I need a 3 by 3 grid to do this. And now I'll write an x minus 1 minus the square root of 5, x minus 1 plus the square root of 5, and I'll fill in the grid, right? X squared minus x plus x times the square root of 5 minus x plus 1 minus the square root of 5. And negative square root of 5 times x is minus x times the square root of 5. Minus square root of 5 times negative 1 is the square root of 5. And what is negative square root of 5 times positive square root of 5? Negative 5. Now, notice that this x times the square root of 5 in the top right cancels with the negative x square root of 5 in the bottom left. That this square root of 5 cancels with negative square root of 5. So, in fact, all the radicals have left, and we have combined like terms x squared minus 2x plus minus 4. Right, combining the 1 minus 5. Now you would still have to multiply that by x minus 4. Okay, now I'll show you a different way to do it, which I'm thinking you're probably going to want to use. And this is the first year I've actually taught this. And actually, if you look in the book, you're going to see a third method that they use that I don't think you would find easier. It involves factoring of the difference of squares. That I think it assumes that everybody is like so comfortable with factoring of a difference of squares that it's trivial, but I know that it's not. So here, we know that we have zeros in this problem of 1 plus or minus the square root of 5. So I'm going to say x equals 1 plus or minus the square root of 5. Subtract 1 from both sides. Square both sides. Right, x minus 1 squared is x squared minus 2x plus 1. What do you get when you square a plus or minus? A plus times a plus is plus. A minus times a minus is plus. So when you square it, actually the plus or minus goes away. And what do you get when you square the square root of 5? 5, right? So here we go. Now subtract 5 from both sides. X squared minus 2x minus 4. Same thing. My bet is you'd probably find that easier than making this entire grid right here. Sometimes even like in the process of going from here to here, we make a lot of mistakes just distributing the minus into the parentheses. Okay. Now the number 8 is you have a rational 0 and you have an imaginary 0. One imaginary, but you can't have one. So what's the other one? If 3 minus I is a 0, what's the other 0? 3 plus I, right? So here's the 3 zeros. 3 minus I, and 3 plus I. And again, the linear factors are x minus 3, x minus 3 minus I, and x minus 3 plus I. So you have to now multiply, and you would definitely start with these two and then multiply the result here. But we can use that same trick that I used on the last slide, right? Actually, we can describe these two zeros as 3 plus or minus I. So let me just set x equal to 3 plus or minus I. Now remember what I did on the last slide? How did I get to the polynomial, the quadratic? Yeah. Remember, we're trying to isolate this plus or minus because we want to square it and see the plus or minus go away, right? So subtract 3. So again, now that we've isolated the plus or minus I, what am I going to do? Square it, square, and square. And x minus 3 squared is x squared minus 6x plus 9, perfect square trinomial. When we square the plus or minus, it goes away. What do we get when we square the I? -1, right? So add -1 to both sides. X squared minus 6x plus 10. So now we need to multiply x minus 3 times x squared minus 6x plus 10. And then you could, again, use the grid or whatever you want for that. And then we're not going to do the number 7, but in the number 7, they've actually given you both imaginary and irrational zeros. So you would have to add, what would I add as the conjugate of 4 minus the square root of 6? Conjugate of 4 minus the square root of 6? 4 plus the square root of 6? What's the conjugate of 2i? It's just -2i, right? It's like 0 plus 2i. The a is 0. So 0 minus 2i, -2i. So you'd end up with 5 zeros for that. We're not going to do that. Now, the last, like I said, there's one theorem that they do have in here that's called Descartes' rule of signs. Descartes' rule of signs was a way to know how many positive and negative real zeros. Not necessarily rational. Could be irrational, could be rational. And it has to do with, you count the sign changes that you see, right? So if you just look at a function and I count the sign changes, it looks like it goes from plus to minus, that's a 1. Minus to plus, that's a 2. Plus to minus, that's 3. And then it doesn't change sign again. That means there could be 3 positive real zeros or less by a multiple of 2, right? So it could be 3 or 1. That would, if you were going through a laundry list of possible rational zeros, it would, tell you you don't have to look beyond a certain point. And then you could find the negative real zeros by finding f of negative x, meaning in every one of these terms, if you put in negative x for x, the even power terms, they're the same, right? Because you take a negative to an even power, it doesn't change the sign. But the odd power terms, they change their sign. And then you count the changes of sign. And again, however many changes of sign you see, it can be that many negative real zeros or less by a multiple of 2. And I think this one ended up being 3 and 1 again. It might help you if you had like dozens of zeros to check. The other two theorems that I remember using are, let's say you check a positive 0, and maybe it doesn't work, but you get all positive coefficients. Then you know there's no zeros greater than the one you just checked, right? Or if you check a negative 0 and you get alternating signs, then you know there's no negative zeros less than the one you checked. Those are tools that we used to use. But again, we're not really going to do that. What I think the SOL tries to get at here, which I'm going to do on this problem, is easier than that. It's much easier. And there's no homework problems that really go with this, but we should at least show it. How many complex zeros do we expect in this problem? 6, right? So I'm going to make, here's a column for complex zeros, the number of complex zeros. Here's a column for imaginary, and here's for real. So we know that there's 6 complex. We know that imaginary zeros occur in pairs, right? Even numbers. So how many possible numbers of imaginary zeros are there going to be in this 6th-degree polynomial? Could there be 5? Not an even number. Could there be 8? More than 6. It can't be more than the total complex. How many could there be? 6 or 4 or 2 or 0. I mean, it has to be an even number less than or equal to 6. So the number of imaginary zeros are either 6 or 4 or 2 or 0, right? Well, if there's 6 complex zeros and 6 are imaginary, how many real zeros are there? 0. They got to add up to 6, right? If there's 4 imaginary, how many reals? 2, right? And if there's 2 imaginary, 4, and if there's no imaginary, 6. That's it. Now, realistically, what you probably do with something like that is you put it in the calculator and you look, and you look for that signature, like how many x-intercepts do I see? Any of them look like they're like bouncing off and staying on the same side. That'll tell me that it's there more than once. That'd help you narrow down how many of each that you might expect. Okay. And what is that? That was the end. But so I don't have my objective slide. Let me do this, because I think it's kind of actually useful. Right. These are all SOLs. Define a polynomial function given its zeros. Determine the factored form of an expression from the x-intercepts. Basically, turn zeros into factors. Describe the relationship between the solutions or roots, zeros, and the factors. Almost the same. Given a polynomial equation, determine the number of real and non-real solutions. I mean, those were all the objectives. Now, the homework, which I obviously didn't save the slide, the homework kind of dances around a little bit. Page 383. Three through 8. Right, those are all the ones like the first one we did, where all you have to say is how many complex zeros are there based on the degree. So it's literally, it's like you do all 6 of these problems in about 5 seconds. You're just writing down the highest power of x. Right. Then we're going to go back to the section about rational zeros, which is 374. And 3, 7, 11. I think those 3 are, I think there's some of these, I'm thinking it's those 3. I just list the possible rational zeros. That's it. The next are find the zeros, meaning make your list and then try them. There's not that many possible, so just do synthetic division, see if you can find a zero. And if you can, then you reduce it, see if you can find them all. 13, 19, 21. And then we go back to 384 and 21, 27, 29. And I think those are, here's the zeros, make the polynomial, right? And it'll probably be one of them, which is like they're all rational, and then it'll be one that has imaginary and one will have a irrational. And that